perspective, also we send a lot of satellite or the spacecraft or rover to explore the outer planet. For example, there's a Curiosity, but the Curiosity itself is still, I mean, to consist of a lot of electronics, and there's a PCB inside, there's an integrated circuit, the building block of the IC, also transistor. So for the NASA perspective, we have to consider about the radiation susceptibility of the transistor. So my project is also aligned with the aerospace application too. So in space, there is an abundance of the high energetic particles in the environment. A typical way to, if we use the solid-state electronics in the very radiation-rich environment, actually radiation upsets the solid-state crystal that ionize the device. So it very often causes a malfunction, and at the same time, it causes to degrade the device. I will explain the details mechanism. And also, on top of it, some planet like Venus, the Venus surface temperature it goes up to high as 500 degrees Celsius. But when we use the silicon, actually silicon itself becomes fully ionized. Even there, regardless there's the electric field, of course, the or not, the temperature itself can ionize the silicon. Then there's no longer functionality at such high temperature. So for very radiation-rich environment application, as well as the very high temperature application, we have to come up with some new device. So for such a harsh environment. So this is like a example of failure what we really encountered before. So various type of event for various type of spacecraft, including satellite and spacecraft. There's an error. Some error is recoverable. Some error are catastrophic. That actually, leads to mission failure. Actually, and then we have to waste a lot of money. So this is the bird's eye view of a transistor. And then transistor, we have a gate, exhaust, and drain. And then actually the channel of the substrate, channel of the transistor is connected to the bulk of the device. And in order to isolate the one device into adjacent device, we used to etch out of the transistor and surround by some insulating layer. So this is the very fundamental building block of transistor. And then there's a material. There's a three conductive materials, gate, exhaust, and drain are very kind of conductive material. And the channel is a semiconducting material. And then insulating material. There's a three components of the material. So when the high energy of radiation or high temperature is around the silicon lattice, actually when this such high energy interact with the silicon lattice, either collision or some heating, it actually it transfers its momentum into the silicon crystal, and the silicon crystal becomes ionized, then leave one free electrons and leave holes inside of the crystal. So I explained that there's the basic component inside of the transistor. In conductor, actually conductor is already full of electrons itself already. So whether or not there's a extra ionization or not, it actually doesn't impact much on the conductor. But in semiconductor, we want that semiconductor becomes either conductive or insulative, depending on the voltage we apply across the semiconductor materials. But when high energy or heat excite the electrons, it actually momentarily or temporarily create some electron-rich condition. So it may cause some soft error. And there's an insulator. This graph is actually stand for the band gap of the material. In insulator, as the band gap is quite large, once this radiation interaction creates an electron pairs, electrons are kind of like a very light material, so it very observed or in this case kind of fast. So it doesn't really matter for the generation of the electrons, but the holes are heavier, and then it's actually bound inside of the lattice. So it often localized, and then it acts as a localized trapped charge. So when this space radiation interacts with the insulating material across around the transistor, the positive charges are trapped, and this density of the positive traps are getting increased over time. So the defects affected in the insulator, it acts as an aging mechanism. So there's a instantaneous error, and there's a cumulative error, which is very relevant to the dielectric, and there's a catastrophic error. Once the energy is too high, it's physically burned out totally. So it's out of my concern as of now. So I explained a little bit of details about soft error and cumulative errors. So when the heavy ions or protons are striking inside of the silicon device, it creates a pair of the funnel of electron holes, or just one pair of electron holes, depending on the mass or energy of the striking the radiation types. So when we create functionality by using transistor, we often use an complementary type of transistor. One is N-type transistor, and the other is P-type transistor. And this is a very basic element called the inverter. So in inverter, we are basically using the very surface of the silicon, but in the bulk region of the silicon, there's a parasitic transistor formed by N-type transistors, diffusion region and P-well of the N transistor, and N-well of the P-type transistor. There's a P-type diffusion region. So there's one NPN bipolar transistor and PNP bipolar transistor, which are cross-coupled each other. So by whatever reason, if there's some trigger in one of these bipolar transistors, actually one of the output current of the one transistor fed into the input of the other transistor, and there's a positive feedback. So when one of these the transistors are turned on by whatever reason, and it enters into the positive feedback, so it becomes a latched state. Then this kind of event causes a soft error. Then the way to recover, this is actually recoverable error. So the way to recover from this kind of latch-up characteristic, the error is just turn off the device, turn off the power down the electronics and power up again, then this phenomenon goes away. This slide shows the aging. Then I explained that there's another type of error, which is cumulative error. And as time goes by, the positive charges can be built up inside the dielectric. And then if these charges are, localized on the surface of the dielectric, surface of the transition side, then these positive charges can act as a constantly and partially turning on the parasitic transistor, because the transistors are formed on the device surface here, but these positive charges which localize in the sidewall of the associated channel, actually it acts as a parasitic transistor that connects to the main transistor in parallel. So there's another gate which is in between the gate region and the channel region, and when the defect or positive charges are trapped inside of the gate dielectric, the role of the gate dielectric is just blocking the channel and the gates, but while transferring the electric field from the gate to the channel, but the positive charges or defects generated in the gate dielectric actually is very close to the main channel surface. So it acts as a scattering center, so which degrade the mobility of the channel. So overall result is seen like this. As time goes by, the off-state linkage goes up because of this, localized high trap in the sidewall, and then reduce the drive current because the mobility of the channel is degraded. And then this kind of behavior is getting worse and worse as time goes by. Then once it shifts too much from the design tolerance, and then the device, the system no longer works. So this is a this is a conventional way to mitigate such a soft error. So in order to remove this parasitic back-to-back parasitic match-up circuits, we replace this bulk region into the ferric oxide, the insulating region. By doing so, we can physically remove the formation of the parasitic transistor. Then this is very common practice for the space application. And then this wafer is also called as a silicon uninsulator wafer. But even in the silicon, uninsulator wafer, we actually see that there's a single transistor latch-out. But there's no latch-up circuits, then the single transistor itself as an N-type channel and P-type, N-type source and P-type channel and N-type drain. And then we just expect that the gate control the lateral channel, but this NPN also lateral type the bipolar transistor with a floating base. Then when the radiation creates the electron hole pairs, the electrons are collected by the VD terminal, but this holes, there's no way to observe. In the bulk, there's like a body terminal that observe any formation of the holes, but the body is electrically floating. Actually, the body is bound by electric on top and bottom, and the P and built-in potential at the left and right. So whatever reason, there's a hole formation acts as a base input current. Then it actually it turns on the parasitic lateral bipolar transistor. So this is today's traditional way to mitigate a single event. Because if we want to reduce the single event, if you want to reduce the ionization, we also the most straightforward way is to reduce the interaction, the volume, the silicon with radiation. So I explained that we use a silicon insulator wafer. Then as time goes by, we migrate into the thick top oxide into more thinner top oxide, which is called the fully depleted SY, and we go as nanowire. By doing so, we can decrease the volume of volume of the silicon channel or sensitive area of the silicon. But if we project this kind of tradition and extrapolate this kind of the trend, then we can encounter that what if the volume becomes zero? Then there's physically no material that never interact with the radiation environment. So then this kind of extrapolation ends up bringing us into the vacuum channel. Then this vacuum channel is in principle equivalent to our very old school type vacuum channel transistor. Then